Hello everyone, welcome back. So in the last video, we saw how to read and write data into the temperature controller. So let's just go online and check. Let me just quickly download this and see what we have done in the last time. So quickly download it. So it's already 25 there, it's 45 here. So this is the value you remember in the last video we wrote into the controller, right? So there is some small change in the program. Let me just download it. Okay. So now you can see here. Yeah, so 25 and 0. So because the PLC wrote 0 into the bus, so it's okay. So I can change this number to any number. Okay, I want 45. So it's immediately 45. I want 20. It's immediately 20. So I'm able to read and write to a device. Read and write to a device. So in this video, we are going to see how to add a second device in the network, and we will also see how to read multiple registers. So here we are only reading one data length. So you can see we are reading one data length and writing only one data length. What if we need to read a floating point register? So in Modbus there is no floating point register. So the only way we can read a floating point register is by reading two consecutive 16-bit registers. So instead of reading just 40001 or 31001, we will read 31001 and 31002, which in turns together forms a 32-bit data, and which in turn will give you a value, which in turn will give you a real value. Okay. So for this we are going to use another device. Okay. So we are going to use a multifunction meter to do that. So the meter we are going to use is called as Lumel from a brand called as Lumel ND20 Lite. So this is a ND20 Lite meter. So maybe if I can show you some images how it will look. Yeah. So we have the exact same device. Okay, we have the exact same device similar to this. Okay, this is a very good meter. It's a Polish brand. It's very good. Okay, so we need the PDF of the network parameters. Let's open that, and let's find out. We need to read the real-time value. That is, we need to read the the voltage of line, voltage of face-to-face, these kind of things. Okay, so let me just open. I think this is it. Okay, again this same thing. So I think this will be the network parameters. So you can see here this is the network parameter. So if you scroll down, you will be able to see the RS485 interface. So it's in page number 37. So let's say, so yes, so you can see the parameters are now starting to list. So we need to read a few registers for this. So here, so these are the Modbus registers. So here you can see the register is that the registers we need is starting from 6000. Okay, 6000 or 7000. We can use 6000. We can use 6000. So don't worry about the 32-bit registers. We are going to read 6000. So if you see this, we are reading 6000. So 6000 is not a valid register in Modbus. So in Lumel, 6000 means it is 46000 or 46001. So there is an offset of 1. So if it is 46000, it is 46001, 46001. So it is having a 1 offset from the value that is listed on the manual. Okay. So let's say I want to read this value. So how do I read now? So let's go to our TAA portal. So the address of this Lumel device is going to be 2. Okay. So the Modbus device that we have here has the address 3. Okay. So this device is going to be 2. What I have done is, you can see there is now another wire going. So this wire is actually going to, this green wire is going to the multifunction meter. It is going to the multifunction meter. Okay. So let's try to read the values. Let's go to TAA portal now. So I already have a read block. I already have a write block. So let's say this is read current temperature, and this is write SP to the temperature controller. Okay. So now we are going to try to read from a third device or a second device. So again, we have to use the same MB master block. We have to use the same MB master block. We should not change the MB master DB. So instruction, so let's go to communication. So let's quickly take it, Modbus master, put it over here. So here let's put this, and here yes. So we have again, now we have to give a request signal. So if you see here, we are using the clock pulse. So the clock pulse has two stages, it has a 1 and a 0. So we use the 1 to trigger the read function, and we use the 0 to trigger the write function. But here I want to read another third device, so then what I can use? So what I would recommend in this case is, instead of using multiple, instead of using the clock bit here, it's better to create a counter sequence with the number of MB master blocks you are using. So how to create that? So let's insert a new network. So because I'm not having more than 2 states here, so I want a third state to trigger this third MB master, and you have to remember that only one MB master should be active at a time. So what I will do is, I will use the same M0.5, that's the clock pulse, but I'm going to give this to a up counter. So let's go to basic instructions, counters, count up. So let's create, say, sequence count. I'm just giving any random name. So there's a reset function and there's a preset. So the preset I will give it as 3. Okay. So whenever it becomes 3, it will reset the counter. So for that I will give the counters reset to the counter itself. So sequence counter reset counter QU up means when it is finishing the up count, it will reset the counter. Now what I will do, I will take the CV of this counter and use it here. So for example, I will put a equal to instruction. So I will go to the comparison section. So you will be already familiar with all this instruction when you are coming to this particular section. So go to the comparator. Let's say I want a equal to function. So the equal to will be 0 of the count up. So count up CV, we need CV current value. So now here, so instead of it giving it like this, we can use the ND20, but we can use the different pulse function. So in the bit logic, we have the p-trig block. We'll put it the inline p-trig block. Just give this address here. That's it. So what happens whenever the value is 0, it will give this pulse to this trigger function, and it will in turn will give a request. Okay, so we will do the same thing here again. So we will put p-trig, we will put a double equal to here, and this will go here, and this is there. So now same thing here, it will be 1. So when it is 1, it will execute the write function to the temperature controller. So with respect to the sequence count function CV. Okay, now same thing we have to do for the third one. So we will add a double equal to, we will add a p-trig block specifically 2, and here again the sequence count value. Okay, so now here I will give M20.2, I will just follow that sequence. Okay, so now it is asking for an MB address, again same thing. So I want to add number 2 because the address is 2 here. This is the next device, so this is the read value from multifunction meter or Lumel ND20 Lite, okay, MFM. So I'm reading value from the Lumel ND20 Lite MFM. So mode it's 0 because we are reading. So data address. So data address, as I said, you remember 46001. You have to give 46001 because there is an offset of 1. Okay, that means what happens here is, so for example, I can just quickly say the example. So let's say in a blank workbook. So the register is like this. So it's starting at 6000, so which is equal to 46000, which is equal to after the offset. So so this will be we can say equal to this plus 1. Okay, so like it will go like this. So sorry, Z 62001. So if the register is like this, so we can say equal to this plus, let's say 4 zeros. Okay. So this will be the Modbus register, and this will be the actual register. So this is with offset. Okay, with offset. Okay, holding register from manual. So this is how the data will. This is how the data will look. So when it is 6000, it will be 46000 as per conversion, and after the offset it will become 46001. So see, this is not a constant thing. This is only applicable to this controller. So if you remember yesterday, when we did for the temperature controller, there was no offset because the data was coming correctly in that data itself. Okay, so here we can say that these two data, so the first two data together is L1 voltage. So it's not one register, it is two registers. It is two registers. Okay, you have to remember that it is two registers here. You can see here L1 voltage is 6000 and 6001. That is L1 voltage. So we need to read two data together now. So here the address will be 46001. The data length will be 2. So now if it is 2, I cannot just give a value. So for example, let me try this MW104. So for your satisfaction, let me do this. So I will download it. And we can also have the option to check whether our count sequence is working as well. So it's loading, load. It's a quick download now, since it's already loaded into the PLC. Finish. So online. Minimize. So you can see here, these two are executing fine. Okay, it's 25, 20. So you can see here the value is 20 already here. It's here. So if I hold the temperature sensor, it will go to 26. So 26. So 26 now. So it will take 1 second delay because of the half a second pulse. We can also increase this pulse of this counter to make it go more faster as well. But you can see here it is not reading anything, but it is showing an error called as 16-8180. Let's find out what this error is. So this is an interesting error. So let's say what this error is. 8180. The error 8180. Let's open the help, our good friend in Siemens. Scroll down and you go to let's say request more data pointer. Okay, where is the error? Okay, it's a status here 8180, right? So we have to find 8180. So you can see it's not value of the port ID. No. What error are we getting? Let me just find it quickly. We are getting 8180. So we have the MB address 2, that's correct. MB mode 0, that is also correct. 460. Okay, let's do one thing. Let me just stop and start the controller, because it should return a different error here. Okay, it's true now. Let's say, yeah, it's okay. So now it's showing an error. It's showing an invalid port ID error. It's a data pointer ID error. Okay, 8180. But it should actually return a different error called as invalid data address value 8189. But it's showing a different error. But let's see. So let's see how to create the actual data type for this. To create an actual data type that is suitable for this is, so let's go offline. I will show you that. Let's go offline. First of all, you have to create a new data block because we need an array. So let's create a Modbus underscore read block. It's a data block. So inside the data block, I'm going to create a read value, read 1. Okay, I'm going to say read one set of value. So that is going to be array of integer. So when I give 0 to 1, it means it will create two values inside. So if I change this 1 to 9, it will create 9 values. You can see here 9 values. So 0 to 9. So as of now we need only 2. So we have to remember that the array size should be equal to the number of data you are reading. It should not be more than that or less than that. Okay, it should not be more than that or less than that. The array size should be equal to the data you are reading. So in our case we are trying to read 2 data. Okay, so how do we link this here? So let's before that you have to do one more main thing. You have to do right click on the Modbus. Right, so let's see here. If you go here, now you can see there is a start value, that's it. Okay, but what I'm going to do, I'm going to change the property of the data block. Right click on Modbus read, go to properties and remove this optimized block access. We need to remove the optimized block access. So remove this and give OK and give OK. So now you can see here you have got something called as an offset additionally here. So previously there was only start value, now you got an offset. So we have to now do a compile of the block. So now you can see it created an address like our normal MW address, MW0, MW2, something like that. Okay, you remember, now you can see that. Now you go to the main block, just click on the data block. So on the details view you get this address, drag and drop this address, into the data pointer. So it will create a pointer address here. So this will only get generated for arrays or for data block elements. Okay, or for data block elements. Okay, so now let's compile the entire program and let's download it. So we just need to download the program blocks here, not much. So let's load it. So minimize this, let's run it. So now you should be seeing proper values here, but we are still having an error here. It's an 8180 error. Let me stop the block and rerun it again. Okay, it's still showing 8180. So let's quickly find out what is the problem. So okay guys, what we did mistake here. So it is showing an invalid port ID, right? So the main mistake we did, I also did not notice when I was creating it. You remember I said we need to use the same data block for all the MB masters. So see here, the data block is different. So that is the problem. So we need to have the same data block. That is why we were getting that error. Otherwise we would have given a different error. So yes, you will also get this error time to time. Okay, you will also get this error time to time. Okay, so that was the major issue here. So hope this will clear the error. Let's see. Minimize it. Yes, that's great. So the error is gone now, and you can see the counter is also working its magic. So let's go into the Modbus read block and see whether some data is coming or not. Okay, let's go into the Modbus read block. Let's go online and see. Yes, great. So we are getting some values. So it is the values are got every 1.5 seconds because of the 3 sequences. So what we can actually do is we can reduce this time as well. So instead of M0.5, if we give M0.3 maybe. So we got a 2 Hertz clock. Yeah, so this should be a bit more faster. So let's download this. This will be a bit more faster to work on in terms of data reading. So we should get the data every 0.75 seconds if I am not wrong. So but it will put a load on the Modbus system as well. Okay, you can see 1, 2, 3, 1, 2 reset, 1, 2 reset. So you have to make sure that no errors are logged on this. Proceed, yes. So now you can see the data is getting acquired a bit more fast. So this is the major disadvantage of Modbus. So the Modbus cannot communicate to multiple devices at the same time. So consider you have 20 different devices and you want to read data from 20 different devices. You have to read it one by one. So let's say a delay of 0.25 seconds. For 20 devices, it will take 5 seconds. So once it reaches the 5th device, it is already 5 seconds. You don't get any data from the first device. So this is the problem with Modbus, and that's why we don't prefer this for real-time process data acquisition. But for monitoring, Modbus is more than enough. Modbus is more than enough. So let's go to the main block again. So, and you can see here we have the data, but it is not a good data. You can say, we can say this data is not giving any meaningful value. The data is not giving any meaningful value. So let's say how to process this. Let's say how to process this data into some useful data. So let's convert this. So you remember here, this data is coming as 216 bits. This you need to merge into a, merge it together into a single double word format or a real format, right? So let's create a PLC tag. So saying called as, let's say, let's give an example. Let's say L1 voltage, for example, and this has to be real. And let's say the data type, the data will be MD200. So let's go to main block. Now, what we have to do is, MD200, right? So MD200 will have MW200 and MW202 inside it. So first of all, we need to move these two values into those blocks. We have to move these two values into that block. So let's open a move block here. So move function. Okay, so let's say I want move here, and let's put, okay, I want two move blocks actually. So two move blocks, and here I am going to drag and drop the data from the first one and second one into MW200 and MW202. Okay, so now let's download it. So what we are doing is we are trying to move the two 16-bit values that we read from our slave device and moving it into a single double word by splitting into two and moving it. Okay, so let's see what data we are getting as answers. So we have, okay, we have the data, we have moved it from our receiving data registers into our actual data registers. Let's go into our default tag table. Let's go online here as well. So we created MD200, right? So you can see the value is still wrong. The value is still wrong. It is showing -300, -4383. So that is still wrong. Something is wrong. So what is the mistake here is, we have to remember that. So I made this mistake deliberately just to show you. You remember the LSB and MSB getting swapped in the Siemens word and double word formats, right? The LSB and MSB will get swapped. So the same thing will happen here. So the 0 word should go to the first word and the first word should go to the 0 word. So this has to be interchanged. So here it should be MW200 and here it should be MW202. So this is what we need to do. So the LSB and MSB have to be swapped. LSB and MSB have to be swapped. So it's here. It's already online. Same, nothing changed here much. But if you go to the tags, you can see now the value is exact. You can see the MD200 is now showing the proper value. So 233 point or 234.233 voltage in the R phase. In the R phase. Understand? So this is how we read multiple registers. How we read multiple registers. So for example, just as an example, let me show you another thing. So if you go here, go to the ND20 service manual. So the L1 is here, but the L2 is somewhere far away. The L2 is somewhere far away. So you don't want these registers in between. So what you can do is you can put another MB master block and just read this address, or the way I prefer is, normally I will read a bunch of data. I will read like a complete set of data from here and I will just read out whichever data I need. So for example, there is a restriction in this device, in this ND20 Lite. So if you go to the manual and see here, so there is a restriction. They have mentioned that you can only read 82 2-byte registers at a time. You can only read 82 2-byte registers at a time. 2-byte means one word. So the maximum I can read at a time is from 6000 to 6081. 6000 to 6081 as per this record. So 6000 to 6081. So 81, yeah, 80 or 81. So this two registers. So which will actually give me the L1 phase, L2 phase, L3 phase, and also will also give me the phase to phase voltage of line 1 to line 2 3 and line 3 1. So let's try reading the total 81 registers together. That is the total of 82 registers continuously. So let's go to our TAA portal. So we need to do some small changes into our blocks. Okay, so let's go offline. So let's go offline, and so this is let's say L1 phase. Okay, L1, L2 and L3. Let's say L1, L2 and L3 phase voltage. So I'm going to read all this here. So you can see here on the Modbus read block, what I'm going to do is I'm going to change the size of the integer to 0 to 81, which means there will be a total of 82 registers. There will be a total of 82 registers. Sorry, we need 81. 81. So 80. So 0 to 81, which is roughly 82 registers, and you need to compile it once to make it generate the offset. Then go back to your main block. You have to do one more thing. You have to change the data length also to 82 registers. So it will start from 46001 to 46083. Sorry, 82 totally. Okay, it will read the 82 registers continuously. Let's compile. Let's download. Let's see whether it is able to pull all this data together. And let's see whether we are able to get all the required values. So I'm just reinitializing the data block for this. Use this. Go online. So we should not get any error. But the data we are trying to read is pretty big as well. Okay, because we are trying to read 82 registers at a time. So let's go to our Modbus read block. Let's go online and let's see whether, yeah. So you can see here now. So this is our L1 voltage. Okay, L1 voltage, and the L2 voltage is somewhere in 6014. So it's 14 here. So these two is the L2 voltage, and if I'm not wrong, these two is the L3 voltage, and finally we need the L1 L2 L1 L3 and L2 L3 values. So that should be around somewhere here. So as per our register list, it should be, yes, 6058. So let's find 58 here. Yes, so this, then this. So this from 58 to 63. So these 6 registers will give me the values of the L1, L2 and the phase-to-phase voltages. So let's find this. Let's do a quick program on this. So let me do it very quickly. So let me create a branch here, another branch here, and let me quickly create multiple move blocks. Move, again move, and let me create in the default tag table 2 more tags. So I need MD400. So let's say L2 voltage, so which will be again a real, so which will be stored in MD204. Then L3 voltage, MD208, L3 voltage, so we know this as well now. Let's go to the main block. So we need to write it again here as MW202 is here, so 206 here, so MW204. I'm just alternating and giving it, and here it will be MW20, it's 4, So we have MW 204, 206, 7. So we have 8 and 11, 9. Yes, so 200, 201, 02, 03, 04, 05, 06, 07, then 08, MW 208, then yeah, MW 210. Okay, so this is the word level address. So as of now, we need to find the register address here. So register address will be 6014. Okay, so that is the 14th register there. 6014 and 6028. 6014 and 6028. So let's go here again. So Modbus reading register 6014. So 15 here and 28 and 29 for the next one. 28 here and 29 here. Okay, so this should give us our three individual phase voltages. Compile, download. So if everything is well and good, this should execute our program and give the three face-to-face voltages of our device. Let's see. So not face-to-face, the face-to-neutral voltage, line voltages. Main block. Sorry, tag online. So okay, so we did a small mistake here. Okay, L2, L3 is here, real. Yes, so you can see here L1 voltage 234, L2 voltage 235, and L3 voltage is 234. So you can see the data registers showing the proper values after doing the proper move function as well. So if you want to make this as a dB, Siemens has a block called as a word to double word merge block. Okay, so this has to be downloaded from the Siemens website. They give you a small source code which can be generated into a program and can be used as a block in the program, block in the software, right? So this is how we read multiple registers in Siemens, and this is also how we read floating point data in Siemens and how we merge it together to form the actual data value. So here we can see two different devices. So with the read write, and here with the, so here we have the read and here we have the write, and again we have the read from a different Modbus device. This is how we do Modbus read from with the multi-register instance. Similarly, if you want to write multiple registers, also same thing. And this multifunction meter does not have much functions to write to, so I'm not going to show you that. But it's similar. You have to create another data type with an array with how many data you want to write to, and you will be able to write the data as well. So with this, we are concluding the Modbus server or Modbus master video. So in the next video, we will see how to use Modbus server functionality in Siemens. Thank you.